Hey everybody, my name's Alex. My group mates Caleb and Nathan. This is our final oral report for our project of matrix and simulation scheduling. Our requester is Fahad Salahet. And our project overview, a little overview on the thing is we're going using an existing code base for LS-DYNA crash simulations, which takes many different types of vehicles, barriers, angles of attack with like many different data points to execute crash scenarios to see how impact works and see data points afterwards based on the impacts. It's written in Python, executed on a Slurm cluster. It takes several crash parameters from key file, like I said before, like the different types of barricades, different types of trucks, angles of attack, so on and so forth. A little problem with the workflow. One of the main ones that we started off with was a slow and inconsistent serial execution with high deviation time for identical runtimes for the same simulation. It wasn't running on the consistently the same time, as well as suboptimal overall runtime of any type of scenario application, which is about 5 to 6 days. We weren't able to do that, unfortunately. We'll go through in detail later on. We weren't able to parallelize as we thought we would be able to, but we were able to manually fix the problem with manually preparing each file for execution through bash scripts. So a little overview on LS-DYNA. Originally, it was it still is a general purpose 3D physics simulation software, but it was originally developed in Lawrence Livermore Laboratory for testing impacts of nuclear detonations around the 70s time. Now supports general finite element analysis on supercomputers. It can use different types of material models for different simulations of different types of varying degrees, as we go in a second. Like what we use for today is automated crashes and occupancy safety for so like different car manufacturers can do different types of their own crash simulations on their own vehicles to see where their like airbags are lacking or to make sure their cars are safe for the public and so they can get ratings and things like that, as well as explosions. So military construction uses like shape charges to see if they're take down the buildings or like any type of things like that, as well as mines to make sure they work to their specifications of what they want, as well as deformation analysis for the same thing and wave and tsunami impacts, so public can see the damage that it might cause in the future for this type of natural disasters.
As on screen, you can see that there is a visualization of a 3D rendering scenario that has been ran through LS-DYNA. We actually acquired this image from the requester himself. This is using his box truck model, in which we can see different parts of the box truck have been outlined by the program and are able to be manipulated by the program as it strikes the barrier or as it hits the wall or something like that. You can see that the truck itself is split into multiple different parts with for instance, like the door, the hood, the box on the back. The wheels are all different pieces, and each of these pieces has to be rendered in order to actually render the 3D scenario, and then it's able to actually do the crash scenario that it needs to. Continuing on, we can look at parallelization obstacles that we encountered with our project. So we actually encountered some significant issues when it came to the requester's requested outcome for this project. It turned out that we were not able to actually parallelize LS-DYNA itself, as it already is essentially parallelized. We think that the requester, the reason he ran into such high runtimes and whatnot, was because of just the hardware on the machine. But we're going to go into that further in another slide. The LS-DYNA has two different execution modes, SMP and MPP. SMP focuses on just a single node execution, in which the requester is currently using this. By single node execution, I mean it is using one PC, one machine, one server, and therefore it is not branching out into a cluster to be able to do the work. MPP does allow a cluster, as it does allow multiple machines, obviously, and it therefore allows cluster scheduling. If possible, we would recommend the requester to use MPP with a secondary machine, but we know that it is not always inside of the budget. Both modes handle their own parallelization, so there's not really a whole lot we can do in that aspect. And then we also just had issues with being able to access the hardware itself. We did not have access to LS-DYNA on Beocat due to some licensing issues with LS-DYNA and how The requester basically formulated it and said we probably would not be able to get it on there. We also didn't have access to the requester's hardware, which made it slightly more of a challenge to understand how LS-DYNA works, because after that we basically had to use research papers and manuals that we would find online for LS-DYNA. It would have been preferable to have some access, but we made do with our solution that we did propose. For future, it would be better. Continuing on with what I was mentioning about SMP and MPP, we can take a more analyzed look at the runtime and some of the issues that might be increasing runtime. So on the graph on the right, as you can see, this is a comparison between LS-DYNA's SMP and MPI parallel methods. MPI and MPP, essentially the same thing. MPI is a interface that allows it to interact with the MPP parallelization. The issue comes is you're going to get an obvious increase in time whenever you're using SMP because you're only using a single node in a single machine. And so therefore you're obviously going to have a larger runtime for your programs. But if you were to get a secondary machine, you can have as you can see according to the graph, a much lower runtime, though that is not necessarily a linear change in the time based off of your CPU count. As you can see, it kind of levels off as you get around to the 13, 14, 15, 16 CPU mark, and only slightly actually increases the amount of time to run. So there comes to a point where you actually get to where you're not actually any good to add more to it. The next thing we can talk about is the existence of single precision executables and double precision executables. We're under the current assumption that the requester is using double precision executables to allow for more accurate data. We didn't actually get a chance to ask him about this. It would be nice to, but it's fine. We would recommend using single precision executable mode in order to let the program run roughly about 30% faster. Granted, the issue comes with that. You will not have as accurate data for your models. And by that, I mean you will have a couple different rounding errors.
So having found these problems with the parallelization of LS-DYNA itself, we had to pivot into the other two issues that Alex mentioned earlier in the form of modularly canceling jobs as well as automating the execution of the existing code that Fahed had, where he was having issues with having to go through and manually change and prepare his files for each run of LS-DYNA. That was taking him quite a bit of time. So the way Fahed had his code set up was it was written exclusively in Python with a bunch of different classes that would route through a myMainCode.py file. This file pulled from a parameters.py file, and that file was then used to supply other subclasses being called by myMainCode.py. MainCode.py had calls for every file, but this control flow wasn't conditional on anything. It was just based off of Fahed's own reasoning on what he needed at the time. What that means is he had a bunch of different method calls to all of these subclasses that would create directories or generate key files or so on and so forth to help him set up his matrix of execution. And then he would just comment out what he didn't want to run at that time. And that was a functionality that I originally thought wasn't necessarily the best, but later on I figured out that's really not terrible for what Fahed is wanting to do, so that was something we wanted to preserve. This mainCode.py would generate key files for LS-DYNA, and what a key file does is it holds a bunch of different keywords and like angle parameters and stuff like that. It holds the initial physics values and what models are being used in your collision simulation, and it just sets those in motion from that point on. Basically, it's the point where we hand off our project to LS-DYNA, and that's where we lose control over parallelization. So he had a class for generating those files, and then several other files that he had, such as his slurm sbatch script, would require fine-tuning the name of the actual file path, and that was something that we figured could be done in Bash pretty easily and done automatically. So in order to migrate his existing code to Bash, we needed to and have this automatic change propagation, we needed to require that that several of his Python files had to be overhauled or completely eliminated. In the case of maincode.py, that can be moved into a single bash masterscript.sh that has a lot of the same functionality. Parameters.py needed an interesting change in the form of instead of hosting the actual parameters themselves, it would grab parameters from a config.sh that was getting pulled into masterscript, and then that formed into an array and fed into the command line of whatever Python code you're executing. And then each class that actually does work in the form of like input files or create directories either got moved directly into bash in the case of create directories, which just goes onto a server and makes a bunch of folders that get used by the execution of LSDyna, or input files, which creates the actual .k key files that get used by LSDyna. Input files needed to be changed from just a class with methods that would get called into a singular standalone piece of code that uses a main method, and so that's taking a little bit of time to do. Finally, Fahed had originally requested that there be something that would allow him to cancel jobs in a modular capacity. We believe this is possible through Bash, since it is effectively a job scheduling language. We have not really thoroughly explored that. Fahed said, after some talks, Fahed said that and the ability to migrate over to Windows seamlessly, the reasoning he had those two requests were as kind of like a tertiary request. It might save him 5 or 10 minutes on a 1.5 hour run. It's not his highest priority, nor could we find an easy way to do it. So in conclusion, we have a good solution for the problem of needing to manually prepare each file for execution in Fahed's workflow, and we successfully diagnosed why Fahed is having problems with long and inconsistent runtimes. But due to the fact that we don't have access to his code or any hardware to run LSDyna, we can't actually really do anything about those two issues. So our solution to the problem currently is just automate parameter passing through Bash and automate the ability of creating a command file, as well as overhauling that Python code to then support those new parameters. And for any references to our findings so far, here are the files. Thank you very much for listening. If you have any questions, you can just shoot them to us over Discord or email, chn@ksu.edu, or Caleb Nehus over Discord. Have a good weekend and have a great end of your semester.